The broadcast is now starting. All attendees are in listen-only mode.
Good morning, good afternoon, good evening, depending on where you are in the world. This is Simon Smith. I'm one of the co-chairs of the Transportation Working Group, and I'm very excited to be here as part of this Transportation Working Group webinar. The presenter today is Oliver Hoehne from WSP Parsons Brinckerhoff. Oliver is a long-term friend and contributor to the Transportation Working Group, as well as the Infrastructure Working Group within INCOSE. And for the past number of years, he's been working with California HighSpeed Rail. And one of the areas he's been working in is the application of RAM, reliability, availability, and maintainability, across the life cycle of that system. So we're very happy to be joined by Oliver today. We had a record number of registrants for this webinar, 55, which is the most we've ever had. So Oliver, the pressure is on. I hope your presentation lives up to the expectations, and I'm sure it will. We are recording this webinar. It will record the slides as well as the audio, as well as any questions that are asked by the audience. And once we're done with the recording, we'll upload that to the Transportation Working Group YouTube channel, so you can share the link with colleagues who perhaps have missed this webinar. I have two other people from the working group steering committee who are helping me facilitate this webinar. That's Rhian Evans and Hamad. Rhian and Evan, Hamad, do you want to just introduce yourself and explain to the audience how the questions are going to work?
Hello. Yes.
Go. All right.
I'll hand over to Hamad. So my name is Rhian Evans. I've been on member services for about 3 years now, and I'm handing over to Hamad, who's going to be taking on the webinars from here on in. So I'd like to just thank everybody who has tuned in over the last 3 years, and all the volunteers that we've had, and I hope it will continue to have as much success in the future. So Hamad, are you there?
Thank you very much, Rhian. Yeah, this is Hamad Al-Jabreen. I'm taking over from Rhian, who's done a magnificent job for the last 3 years. I hope I live up to the expectations, which probably have been raised a lot by Rhian. Anyways, I'll be helping with the questions from there onwards. So the questions will be, if you know, we know you probably have a lot of questions to pose. We'd appreciate if you kept them till the end. So there are two ways to pose questions. You could raise a hand to pose the question, and that you will find it in the attendees section. And then you could also raise a question. There's a question section, and then you could write the question in writing. And then whichever way, I mean, if you raise a hand, then we will get back to you, and then you could raise your question in voice. And then if you raise a question in text, then we'll read out the text, and Mr. Oliver will answer. Switching back to you, Simon.
Great. Great. Thanks, Hamad. Yeah, I don't have much more to say, other than to go on record to thank Rhian for the work you've done over the last 3 years. You've been a really excellent addition to the working group, and I'm happy that you're continuing your involvement, but just in a different role. So, okay, without further ado, we will hand over to Oliver and get going.
Thank you, Simon. Good morning. As Simon said, good morning, good afternoon, good night, wherever you are. Thank you for your interest in the webinar. And just as a little opener, not even an hour before the webinar, one of our team members actually had a computer crash. And but we actually are here and we are giving the webinar. The webinar is available. We had a plan B. We have redundant systems. So this is exactly what RAM is all about. So let's go into the details of the webinar. So the intro slide. So what I'm going to talk about today is first of all I want to give some acknowledgments, give a very brief overview of California high-speed rail. But then in my experience in the past, RAM really is something that is not well understood by many. And so I want to give a little bit of an overview what RAM is, and I'm using an example that some of you might have seen already. And then going into the RAM approach on high-speed rail, both on the program level but also on the project level. And then at the end I'm going to summarize but also show some of the lessons learned we had in the past. So before I start, I want to give some acknowledgments. So RAM, you probably, the ones who know me, probably know me more in the background of integration management of E&D. So about a year ago, I became responsible for the topic of RAM. But high-speed rail is already going on for several years. So there were people before me and still being there that have set up the whole RAM program. You know, the one actually in charge was Ebro, and I still work with David and Paul making RAM happen, and on the program level. And also, some of you might know Alan Kwasi. He's actually the infrastructure working group lead. This is a picture from him in Scotland at BIS. We had lots of fun. And he's the one who has to suffer from all the things we are doing basically on the contract level because he's the first civil contract that's being implemented. But I'll share some more details with you later on. So let's take a brief look of California high-speed rail. High-speed rail is the first true high-speed rail system in the U.S. Construction has started already. Phase 1 is going to be between San Francisco and Los Angeles in under 3 hours by 2029. The full build-out, what we call Phase 2, is about 800 miles, up to 24 stations and operating speeds of 220 miles per hour. For ones not listening in, not from the U.S., it's about 350 kilometers per hour. So the way it's being built, it's actually a similar approach to the highway system that was built in the 50s. Started building where you get the most bang for your buck if you want, but also where you can build a lengthy segment where you can actually that you can use as a test track. So we start building in the Central Valley. Basically where it says initial operating segment, and then build to the north. And it's going to be called, or it's actually being called Silicon Valley to Central Valley. So it's actually valley to valley or V2V. It's going to be the backbone of a high-speed rail system, 250 miles. And it's going to lead by building out to the north and the south to a full high-speed rail system in the coming years. At the same time, because we tie into existing systems already operating in the north and in the south, namely the Caltrain corridor and the Metrolink corridor, there's already some investment underway. For example, the electrification of the Caltrain corridor, because if we're going to come with our trains, it's currently not electrified, it would not work. And so if you go to the high-speed rail website, you will see updates on construction. So these pictures were taken from the high-speed rail website. This is the big picture is actually a video, an animation of how it's going to look like. But even if you can see already with the Fresno River Viaduct, actual infrastructure is being built already. And every day more is being added. And we have 3 active civil contracts already for a length of about 120 miles. Anyway, let's talk about RAM. RAM itself. So what does RAM really mean? And even if we are proud that we can say it means reliability, availability, maintainability, what it really means is a system not working. I personally like to compare it, or I explain it by saying if you had a car and your car works for 10 years and you don't really have to do much other than changing some tires or oil, it's a pretty reliable system. And what we, as a common term, what we use for that term is actually quality. It's a quality car, right? But if you buy one that breaks every other day and it's not working, then you actually don't have really high quality. So this is really the way I see RAM. So you have systems not working, right? Actually, where I commute my train station for over half a year, I had the same view. The escalators were not working. people being annoyed, standing there waiting for the trains, even worse, having train getting stuck in the middle of nowhere, you have to get off. And so if you read articles, what it says is that unreliable trains are even more hated than slow ones. So what's the point of building a high-speed rail system that is really fast if it's not reliable, right? So this is really the underlying assumption of RAM. And also what you see here on the next picture, those are pictures taken from Germany actually, and those are real high-speed trains. And what you see here is that the number of passengers had to be treated by medical personnel. And the reason was actually because the air conditioning didn't work. So actually in quite some months in the summertime. And so what RAM means, this is why it's often referred to as RAMs with an S at the end, is that if something does not work, it can easily or quickly lead to safety implications. So now imagine Germany is not known for hot summers. Imagine going to the Central Valley where you easily see 110, 115 degrees. So let's use an example. This example I've taken from a website. It's called Second Avenue Saga. It's all about transportation systems, and it talks about an escalator in Washington D.C. If you have ever seen them, they're very long, very steep, and they're very known for not being very reliable. So the example being used here says that the Metro's escalators average 153 hours of revenue service before they break. And if you do the math, 24 hours, that's not even a week. And then it takes 14 hours, so over half a day, to fix them again. And then, it goes on describing why that is, poor maintenance and whatnot. But if you now take the RAM, the R, A, and M, the reliability can really be expressed typically in mean time between failures, MTBF, in this case 153 hours, and the mean time to repair, the maintainability, is 14 hours. And so what really those two now are being combined into what the availability is being expressed in percentage. And the frightening part is if you do this math, it comes up with over 90%. In grade school, that would be an A. So just imagine if your car would let you down every week for half a day, I think we would not call this a reliable system. So what can we do to improve availability? There's two things we can do. So obviously, having MTBF and MTTR to play with, the first one is we can improve reliability. So if you remember 153 hours, so just fiddling with MTBF numbers from 153 hours to 266 hours, basically making it work longer, would bring us already to 95%. Or even going close to 1,400 hours, you would come to 99% in terms of availability. But you can also do it the other way around. You can say you can improve availability by improving maintainability. So leaving the 153 hours intact and just playing with 14 hours, so bringing the 14 hours maintenance down to 8 hours would bring us to 95%, and bringing the 14 hours down to 1.5 hours would bring us to 99% availability. So if you now look into how an escalator is broken up as a system into subsystems, you can say that the escalator has an electric motor, a drive gear, a handrail drive, it needs some power supply. And so by just playing with, let's say, 5 different components, if you want to achieve, sorry, I have a little copy, I'm sorry. If you want to achieve the 91.6% availability, you can't just apply the same number to all the subsystem elements or components. You have to play with, you have to use higher numbers because they break. Obviously now, if you have several elements breaking, you want to make sure that even the sum, and not actually not the sum, it's a product of all those elements breaking, so gives you your system availability. So I did the math backwards. So now every single one needs to have an availability of 98.26%. And that's just for 5 components. So let's look into a couple of scenarios here. So the first one we just looked into, if you want the escalator to have 91.6% availability, every system element needs to have 98%, as we looked into. And what I see quite often is that it's being confused, the system and the subsystem, or the system element. So if we confuse, let's say, the system or subsystem availability of 98% and apply the escalator number of 91.6%, already we would achieve only as an escalator 64%. So the numbers drop very quickly if you're not careful. Also, if going back to the first example, if we use 98% for 4 components, but use for the electric motor only 64%, then it would drop even further. So from 91 all of a sudden to 60. So really the lessons learned here is that one subsystem can easily break the system availability. And even if you try to fix it, going back to the second scenario where we achieved 64%, if you take the electric motor and make it redundant, so you have 2 motors with 91%, you actually achieve for the redundant motor now 99%, but it doesn't do you any good. Instead of 64, you achieve 69.9, almost 70%. But really what it means is, if you mess up somewhere and try to make it up later on by putting in one very, very good component, it doesn't help you either. So the lessons learned from this exercise is really that one subsystem alone cannot make, but can easily break the system availability. So let's look into what we're doing on HighSpeed Rail on the program RAM approach. So what is our guiding standard? We are using, we have several, but one that is really, really helpful is the EN 51-6. That's a European standard, European norm. And it's about railway applications. So it's really applied to trains, what we do most of the time. And it talks about RAMs, as you can see, not only the RAM, but S. And it has a system lifecycle approach. So for every systems engineer, I guess our heart, actually beats a little quicker if you see a lifecycle approach. And even better, going on the next slide, it actually has a V model in there, believe it or not. Yeah. So now you can see all the steps. You see concept, system definition, system requirements, apportioning, design implementation, V&V, you name it, right? So for every single one of those, in the EN 51-6 standard, there's now a description of those lifecycle phases. And the ones I highlighted in red are really the ones we are focusing on the program level. So for example, on the concept, in the concept phase, we have review previously achieved RAM performance, consider RAM implications, and so on. I will not be able to talk about every single one, but I pick a few, and we'll show you some details. And then also, if you're familiar with the SE handbook and Code's SE handbook, very similar approach. Now, every single phase, we would call this a process, right? Describes now objectives, inputs, and they didn't call it outputs, they called it deliverables, and instead of requirements, we call it activities. But it basically describes for every single one of those steps along the life cycle what should be done. So let's look into some of the RAM program considerations we have. So what you see here is a typical cross-section, and from an integration perspective. This is actually a drawing I prepared once with a couple of people on HighSpeed Rail, overlaying all the various elements. And you can see embankments, you can see system elements, you can see the train sets, electrification, you name it. Anyway, this is what we are trying to build at the end of the day. So we start out with infrastructure contracts, right? Those are given away individually. We're gonna have to run train sets in there. We have track work and systems contracts. So track, pretty clear, systems, wayside, signals, electrification, you name it, communication. We're going to have a train operator contract, and we're going to have station contracts. And that's not even all, it's just the main, focusing on the main. So this is for the cross-section view. And if you look into the longitudinal view, what we have along the alignment is we have obviously the embankments you just saw. We have what we call aerial structures. We're going to have tunnels. And then what we call the bookends, basically the end, where we tie into existing railroads. We have the Caltrain corridor, Metrolink, and then we have to tie into existing systems. So we're going to tie into existing power supply. We want to utilize some of the existing seismic detection systems that's available in California. We actually have to tie in to also provide intrusion detection from other railroads, but also to other railroads. And so all of this makes it very complicated. And if you want to present it basically this way, that you say you have a high-speed rail system, which is basically breaking up into the main components, and the shaded areas is really let's say, the core high-speed rail systems, and the other ones are systems. If you're familiar with the term system of systems, I would have to tie it into other systems. And now applying, if you look into the upper right corner, basically saying now we have a number of subsystems. So if we, for example, said, hey, let's have every subsystem, let's say infrastructure, train sets, track, you name it, 90% availability, and you do the math, the system, a high-speed rail system, would only end up at 53%, which is really bad, right? Also, if you actually just recalling what we are applying, what we heard before, if everything came back perfectly, which will never be, but let's assume for 1 second, and only one, let's say, delivers 75, then the the product of all is still only 75, right? So that's one of the things we have to think about. And also, if you recall, going from 153 hours to almost 1,400 hours would bring us from 91% to 99%. But just look into the numbers, 153 to 1,400, it's almost a factor 10. And the same applies actually with maintainability, going from 14 hours to 1.5. So in order to go from 91.6 to 99, you have the goodness, the quality of what you're building has to be almost 10 times as much. So that is something you will never ever achieve if you don't think about it up front. So so this is basically what we're doing, right? Just saying, okay, so what is it we're trying to do here? What do we want our high-speed rail system to look like? So most of you have seen this before. If you take availabilities of 99, 99.9, and then calculate the number of hours per year, 8,760. Then you can basically based on the availability, you can calculate how many hours the system is down. And in order to make it a little bit more, let's say, tangible, I also broke them up into how many downtime hours per week, but also per day. So basically, the 91.6% would mean, on average, that 2 hours a day our system would not work. And is that acceptable? I guess not. Right? The answer is pretty clear. And so what we're trying to achieve here is to determine of what is it what we're trying to do on the high-speed rail system as a whole, and then what does it mean to every single contract we are releasing, right? To infrastructure, to train sets, to track and systems. So and also again, whenever you talk RAM, it's really difficult sometimes to get your point across. Even if you explain this as I just did now you're dealing with percentages. What do percentages mean? What does 99% actually mean? So applying it to our ridership, which I took from our business plan, you will see that the ridership for phase 1 in 2029 is 37 million. So if you have a 99% availability, which is actually pretty high for a system like this, that means you would have 1% unavailability. And of 37 million passengers, this would mean that you still have 370,000 passengers potentially be late per year or missing the trains. And on average per day, that is 1,000, right? And so and that's a good number, by the way, yeah? It's only very important that you can communicate clearly of what we know. This is what it means. So please sign off here, yeah? And the 5,100 potentially late on this station stops, it's a formula that you will not see here on the slides, but this is really what it means. So 14 per day, 14 train stops or station stops would be either late or missed completely. So let's talk about previously achieved RAM performance. So if you want to, what we do is we apply a top-down and bottoms-up approach. So if you take the high-speed rail system and break it up into infrastructure, tracking systems, train sets that you have seen before, let's just look into the tracking systems. Tracking systems breaks down into track electrification, automatic train control, communication systems, then the train control and into office equipment, wayside equipment, onboard equipment, and then the wayside equipment again to track circuits, switch machines, signals. There's many, many more, right? So top-down is really what are we trying to do? What is it we are trying to accomplish? And top-down is really is that a number out of a sky, blue sky? Is it something? What can realistically be accomplished by utilizing commercially off-the-shelf equipment and what has been done before? So one of the first steps you can do is you can look left and right and say, geez, I mean, somebody else built already high-speed rail. So let's take a look what they did. And that's exactly what we did. So what you see here is a Shinkansen, it's Taiwan high-speed rail and other systems. And they have a very, very similar structure. It's obviously not always exactly the same miles. They have a number of same trains, but you get an idea of what they can do, right? And so specifically for Taiwan high-speed rail, that's a mix of European and Japanese technology, and they did a lot of work already. I can't share all the details here, but basically they had a RAM requirements analysis report. They looked into a reference system, and that was actually the Shinkansen system. And then based on that analysis, plus other systems we looked into, we could identify what's the typical, but the number we are focusing on, the availability is actually the on-time arrival achievements, OTA. So then we tried to harmonize the numbers, so we achieved a corridor of low and high OTA or on-time arrival numbers. And interestingly though, is if you look into the Shinkansen, there's two numbers from 64 to 82, and then from 99 to 2001. Those are the numbers being available, and they dropped significantly, right? And then you would say, geez, I mean, specifically the Japanese system, what happened? And they were privatized. And so that's actually lessons learned I will talk about later. If you have to pay for things, all of a sudden you might think about it twice, right? Is it really worth spending so much money on a system? And then, but basically what it does is if you lower your investments, you get what you pay for at the end of the day. So those OTA numbers are the basis for our top-down approach. And then also what we did is we, just using the same graphic again, going bottom-up. So in this case, what you see is a picture actually from Shinkansen high-speed train system. And because of the turnouts where you switch track from one to, let's say, a station track or so, they have to be so long in order to have long curves that one switch machine just doesn't do it anymore. In this case, I think it's actually 7 switch machines they need just to move the blades over. And again, if one fails, well, you want to look into your RAM numbers. And so what happened then is for all the equipment, basically we had a system breakdown, all the equipment, all the pieces, and then our team ran the numbers of what has been done before, what is achievable. And then at the end of the day, what we did is we used our top-down and bottom-up approach to say, okay, this is feasible and a reasonable number that we think can be achieved within the constraints we have. So I'm not gonna talk about the actual number we use, but I will show you some of the targets we have set for other contracts. So let's look into RAM requirements, RAM apportioning. Those are all things that the N5216 actually pointed out. So what happened now is looking into basically the system that we know what our system number is. Now we can determine what does it mean to every single subsystem. In this case, actual contracts, right? So let's look into the train sets. So what happened now is the train set contract is actually publicly available. If you want to go to the High-Speed Rail Authority website, under contracts, you will find this. And so there's actually a lengthy section talking about RAM. And they have the RAM targets. It talks about the RAM requirements we are trying to accomplish, applied to high-speed rail, to the train sets of the rolling stock. It talks about following the EN 126 standard, and that's actually a part 3, which is specifically tailored for rolling stock. And also we have contractual enforcement. So not only do we say this is our requirement, but we have something in place that's called availability-based payment. So if a train is not going to make it as advertised or as promised, let's say on the positive side first. The contractor will be paid for trains showing up on time, and there's a certain leeway given. If you can read the fine print, it says allowable number of missed trips. But for each missed trip in excess of the allowable number of missed trips over a 10-day period. Actually, in this case, it says $24,500 will be deducted from the payments. So there is a strong incentive for the contractor to build actually a reliable system, because they will only get paid if their trains show up on time. So let's look into the actual project. In this case, I showed you train sets, but we haven't released the train set contract just yet. However, we are working already with 3 contracts on the infrastructure side. So let's take a look into how RAM is applied to infrastructure. And specifically, most people have seen this, applied to systems, to really complex things, but infrastructure is fairly new. So just looking into again our breakdown structure, looking into infrastructure on the left side. And infrastructure really is at grade. We call them at grade, which is embankments. We have aerial structures or bridges. We have tunnels. And tunnels can come in various shapes and forms, whether it's like the subway style in New York, or there are mines, or basically drills, boring machines. But at the end of the day, they have to work. So what happens is every contractor, every RAM contractor, not RAM, actually every civil contractor gets 2 main documents. One is the contractor RAM process requirements, and then they have contractor RAM system requirements. The system requirements are really part of what we call design criteria, and the process requirements really, if you can read it, the first one refers to CFR, to bridge safety standards, and the second one refers to the EN 5126 that we talked about, right? So let's take a look into what those roles and responsibilities are and task deliverables for the civil contractor. So basically, document your RAM requirements during the design and construction. I'm highlighting just a few. Allocate those requirements to subsystems and system elements. Tracking of RAM allocations following the V&D process. I'll show you an example in a couple of minutes. And provide us with deliverables at certain times along the way to make sure that we can see actually making progress. So looking into the table, just looking to infrastructure, and it actually says infrastructure availability is 100%. And technically everybody would tell you 100% is not achievable, but in this case it's actually different, and I'll show you in a minute. So so if you now look into infrastructure, you have seen this picture before, complete alignment. So now we have the RAM program numbers. Sorry, and then we have the apportioned RAM targets for infrastructure. So as you can see in the table or the listing below, allocation 2, right? It says infrastructure in yellow below. So now those 100%, it could be a different number for systems, have to be allocated, right? And what you see on the left side is that we have 3 active contracts with 3 red boxes. The first one is CP1, second one is what we call CP23, and the third one is CP4. And what we want the contractor to do now is to take those infrastructure requirements written in the contract and apply and further break down their system into basically sub-elements, subsystems, you name it. And you see, again, guideway at grade, aerial structures, overheads, it's basically bridges, trenches, cut and cover tunnels, underpasses, you name it. And then allocate those requirements, RAM requirements to those system elements. And if you recall this picture, how we can improve availability by improving reliability or maintainability. The reliability for infrastructure is really 100%. And what does it mean? It means we cannot, as in the, let's say, IT world, just provide a redundant server. We cannot build redundant bridges. It's just cost prohibitive. So what we do is we ask for bridges or for infrastructure to be built with a certain design life. So the infrastructure must not fail during the design life. That's really what it means. And what it also means is during the revenue hours. And maintainability is really what it means is now the only thing we can really play with is a preventive, or preventive means basically proactive before something fails, and corrective means that something has broken and you have to go out there and fix it. Basically preventive maintenance to be performed between or during the non-revenue hours. And we have, of the 24 hours a day, we have 5 hours of non-revenue service between midnight and 5 a.m. So first, we build infrastructure that does not fail, and secondly, in order to keep it up and running, we are allowed to go out there and perform maintenance activities, but it has to be done during the 5 hours of non-revenue time. So having that in mind, now what we did is we created for reliability, we created design criteria. And again, not sure whether you can read it, but it says under structures, for example, 100 years, for site and earthwork, 100 years, and others are a little bit less. But it also means, for example, if you look into structures where it says, well, it actually doesn't say here. It's somewhere more in the details. But it actually says movement, expansion joints bearing 50 years. So we got to be able to replace those during the 5-hour window we have. And how this is being done, I'll show you also in a minute. And then, as you can see, with a number of deliverables now, they are focusing, mostly on maintainability. Almost all of them, this is really the thing we can work with, right? So we have a historical product maintainability report, maintenance manuals, and you name it. So let's look into the maintainability, because it's really the most important aspect that we have. If you go into the EN 5126, actually part 2 now, this is a picture I took from there and redrew it. In RAM, what you define as working would be the up state. So something is working just fine, and if it breaks, it's called the down state. So it goes from up to down, not working. And what you try to do is within a certain amount of time to bring it back to service. So for example, your car, if your car broke, all the time you cannot use it would be considered downtime. And so if you look into the arrows, it says failure occurs, right? And then you have corrective maintenance, preventive maintenance, and you have ready for service. So if you have preventive maintenance, basically you don't have to wait until something breaks. You basically go in there, you know exactly when you have to show up. Hopefully that's within the 5 hours. I don't know, you lubricate something, you replace it, you inspect it, and then it's ready to go. With corrective maintenance, it's a little bit more difficult, because if you look into the bottom, it says detection and travel to site. First, you have to know that something broke. So that's the detection. And then often you just realize something is not working. So then you have to travel to wherever that is. It could be in the systems world, a server room, a station, but in this case, infrastructure, 800 miles, that might take a while, right? Then you arrive at the site. Then you have to perform failure analysis, inspection, whatever, saying what actually broke. And then sometimes it's something that you didn't bring with you, so you have to think about spare parts and tools. Do you have to go back to your truck? Do you have to actually go back to a maintenance facility, maybe even bring heavy equipment? And then you can start repair or exchange. And then you perform a check or test inspection that it works, and only then you can bring it back up to service. So all of these activities could be the 14 hours that you saw from the Washington, D.C. metro. But the idea is to bring it down to an acceptable level, right? An acceptable, as you could see, what is our availability? The only number we really can play with is the maintainability for infrastructure. So what does it mean to our contractors? So if you now take the detection, the travel to site, the failure analysis, spare parts and tools, right? So what we do for detection, we put in maintenance, roadways, walkways. We have inspection, maintenance, access areas, holes, hatches. Travel to site, we have a 2.5 mile interval where you can actually go from the road straight to getting access to the high-speed rail system. We have access roads, parking, you name it, right? So you get the idea. What we're trying to do is to make it reasonably acceptable to get to the site quickly, have access to whatever needs to be inspected and repaired in order to keep the maintainability time down or as low as possibly acceptable. So, what are we asking the contractor to do now? So obviously we wrote requirements in the contract. You shall do this, you shall do that. But one of the things we ask the contractor to do is to perform what we call historical product maintainability. So looking into, similar to what you see in the upper right corner, where we looked to complete systems, now we ask contractors to say, show me how this is done elsewhere. Comparable high-speed rail systems, other rail systems. And so the contractors perform basically for the types of products they build, whether it's bridges, trenches, tunnels, utilities, you name it. How this is typically done. And so this basically gives us what I would refer to as a best practice analysis overview. And so here's an example of what you can see at the right corner, it's a breakdown of, again, aerial structures, overhead structures, trenches, guideway, and then each bridge, for example, aerial structure is broken down into the superstructure, the substructure, the bearings, expansion joints, you name it, and then the superstructure is broken down into the reinforced concrete deck, derailment walls, you name it, you get the idea, right? It's typically systems breakdown, and then for every single one, there is, we look into 3 different things. We look into basically the day-to-day inspections and also, replacements. I apologize, I have a cold. Anyway, and then what we do now is based on the requirements of a contract plus the best practice analysis, what we ask the contractor to do is to come up with what we call a RAM maintenance concept. Basically saying also, so based on what you shall do and how others do it, tell me what you're going to do. And the tricky part here is that the contractors, the civil contractors, are not responsible for this system later on to maintain. They will go away, they will hand over, so their incentive is not necessarily to make it maintainable. If they have a choice between making it cheap or making it maintainable but a little bit more costly, you can probably figure out yourself what a contractor would typically do. So in this case, what we're trying to do here is saying, you tell me how you would maintain this if you were responsible. And then it's obviously reviewed on our side. And then that maintenance concept finds input into the design and construction. And then at the end, we perform maintainability demonstration. So how would this work with maintainability demonstration? This is now looking into the future. We are not there yet. So this is an excerpt from one of what I just referred to as a best practice analysis. It describes, for example, repair action times vary by specified actions, blah, blah, blah. But it would say if bearing replacement is required, then these steps would have to be performed, right? It says once a 5-hour work window begins. So it's a step-by-step. It's almost like a maintenance concept or concept of maintenance. And it says in there in the language, jacks would be used to lift the superstructure. So, so this is what the maintainability, basically, this is what the best practice analysis says. This is what our maintenance concept says. And this is how we want to, perform maintainability demonstration. And then using what we call our V&D process, now we look into the actual submittals from the contractors. And in this case, it's actually, as you can see, it's an aerial structure. And then it would actually lift to a jacking point. You see, so what we do is during design and construction, we make sure it's actually being implemented, and then we will use the very same documents and have a contractor demonstrate to us that it's maintainable. If it works on paper, great, but we also reserve the right to actually ask the contractor to do this in practice. Anyway, that brings me to the summary and lessons learned to the end. So as you know, as already the flyer said, RAM is really very abstract and difficult to understand, and the best way for me to explain it is the quality of the system, and that really leads us to the next one. We have in project management, you would call it scope, cost, and schedule. In systems, I like the 3 Ps: the people, processes or procedures, and the product. So in this case, a lot of the effort has to go into the education and training. So we had endless sessions, within the program, with construction management, with contractors, independent checking engineers, and the way we do it is workshops, walkthroughs. We basically give similar presentations to what you see here. We should walk through a contract, and this is what it says. This is what you should look at. These are the deliverables. This is what it means to you. This is what we expect you to do, and that has been quite helpful in getting there. Also, I touched on it already, a strong oversight is required, specifically if the one who is building something is not the one who has to operate or maintain it. So there's always, the short-term versus long-term considerations you have to keep in mind. Contractors are not necessarily interested in giving you the best solutions. They want to get it done quickly, they want to get it done in budget, and want to be done with a project and, cut the last check and then move on. And also, some of the issues we ran into is infrastructure is different from train sets and systems. So if you give a contractor a typical RAM spec from the systems, it's not going to work. We had some painful lessons learned. So all I can tell you is this is what INCOSE often says: tailor, tailor, tailor. Make it applicable. Don't make it too complicated, but also not too light. Having said that, that brings me to the end of my presentation, and I'll hand over to you, Simon, and then Hamad for any questions.
All right. Well, thank you, Oliver. That was that definitely lived up to expectations. A very, very interesting, thought-provoking presentation, and I thought the slides were very very easy to follow. You made what is quite a dry subject actually very visual and engaging. So, well done. Good job. Okay, I'm going to hand over to Rian and Hamad to field the questions.
All right. Thank you very much for this interesting webinar. Has been definitely something interesting. Let's go to the written questions, and then first, Mr. Amir Tosi has asked, do you consider timetable reliability / robustness and other operational factors in calculating the OTA, the on-time arrival?
That's a good question. So can you? I'm not sure I fully understand the question. I have to say, timetable robustness is in my eyes.
Oh,
let me translate timetable. Yeah.
Yeah. Let me say
Okay.
my interpretation of it and see if Mr. Amir can also come into the line. If I can understand it correctly, is that if the timetable is reliable, the timetable itself, is it reliable or not, or is it robust or not? So, Mr. Amir, if you could confirm, I will unmute you now. Hello, Mr. Amir.
Hi, thanks. Yeah, hi. Can you hear me?
Yeah.
Yeah, just have as you said, basically, it's a very interesting presentation, Oliver. I was just wondering, well, on top of all of those technical, basically reliability factors, do you consider where does the timetable sort of factors and parameters come into kind of your calculations of on-time arrival? Basically, would you consider that timetable was running perfectly and you wouldn't get any problems with the timetable, and it's just when you focus on OTA, it's just the technical failures that you would factor in your calculations? Thanks.
So the way I understand it is that saying if a timetable itself, so let's say the timetable has to be correct in itself in order to measure successfully the performance of a contractor, right? And so is your question related to, it could be that the timetable is wrong or it's not reliable because it was really optimistic, let's say the headways?
Yes. Well, one of the factors is headways or station dwell times or things like sectional running time variance, driving style, things like that, basically.
Yeah, and so we have actually quite a large team even available that we have used also in the past, not only this, also in other projects, where we simulate the train runs, the timetables, where trains pass, as you said, the dwell time, the turnaround time. But I can tell you, the opening scenario, what I showed you, you probably recall the ridership for 2029.
Yes.
So the ridership of a first segment is 7.5 million assumed. And that is really only, if I remember correctly, one train every half an hour during rush hour and every hour during non-rush hour. So I think we can safely assume that this is achievable. And also the other ones, we are not at capacity at all at the beginning. Is that what does it answer your question?
It makes sense. Yeah. Thanks very much.
All right. Thank you very much, Mr. Amir. Very interesting question indeed. Now switching over to Rayan, I think.
Hello.
Yeah. There you go.
Yeah. So then we have Jörg Lagent. I'm sorry if I've pronounced that wrong. Who has raised a hand and also written the question. Jörg, I don't know if you would like to read your question out. I will unmute you and see.
No, Rian, that's the written question I think is more than adequate, so I don't feel a need to participate. Thank you for the...
I can read it out, no problem. Thank you. Okay, so the question, is it George? Sorry. The question from George is, you should be able to see it as well, Oliver, is so that 2 hours a day on a system would not work, or is it 5 hours of non-availability per day to cover this? I'm not sure if this is a couple of questions. Well, it looks like a few questions actually. Let me see.
No, it's maybe I can just answer the first one.
Yeah.
Every day, anyway. So we have 24 hours a day, right? And of those 24 hours a day, we have 5 hours of where we do not run any trains. It's really shutting, switching off the lights and maintaining the system. And then we have another hour a day where basically trains are being positioned. So we have 18 hours of what's called revenue time. And of those 18 hours, we have 6 hours of rush hour and 12 hours of basically non-rush hour. And those 18 hours are the ones which basically is our 100% of what we measure availability. Actually, I would even go back and say the 19 hours. 19 hours. So that becomes 100%. And during that time, the system has to operate as intended. I'm not sure. George, is that the question you had?
Sorry, let me just unmute him again.
No, you're going to make me go back to my notes.
That's okay. There were quite a few elements to your question, George. I don't know if there's something that summarizes it all.
Rianne, sorry to jump in. It's Simon here. I'm just looking. We have 9 minutes to go until the end. We have quite a few other questions to get through. So what if we can, George? Unless you have another burning question to throw to Oliver, I would suggest we move on to continue working through the other questions. George, are you okay with that? Okay,
I guess a common theme looking at these things would be to ask how much, just one of them there, is there a systems engineering management plan?
What does it have to do with RAM right now? Okay, so to answer the question, so we actually do have, let's say, we do have a number of sub-plans. So we have a RAM program plan. We have other plans, as you know, the V&V and V. So we do not have one that says Systems Engineering Management Plan, but we have for every single of the subdisciplines we have those available.
Okay, so I take that as a no. Does the California High-Speed Rail project have a Systems Engineering Management Plan?
George, what are you doing? It's, I will be at the IW. Let's talk about this offline, okay? We're talking about RAM today.
Okay, I misunderstood. I apologize.
Okay.
So let me just answer the question. So we do not have, George, we do not have a plan that has a title Systems Engineering Management Plan. However, we have many sub-plans, and one of them is a RAM program plan, which is exactly what this is, the Systems Engineering Management activities applied to RAM. I hope that.
All right. Thanks for the question, George. Let's move on to the next one, Rianne.
Yeah. Great. Hamad, can you read out? I just have lost the questions for you for a second.
Mr. Bill Brown has nicely asked. Can you explain further how to ensure an effective turnover from the OEM warranty period to the operator agency maintenance period?
Well, that's so we probably have to take one step back, and I have to explain how this is going to work. So we have the civil contracts right now, and then we're going to have what we call a track and systems contractor, and that track and systems contractor will have to operate and maintain what in Europe you would call this the infrastructure, but it includes actually the systems. And then we also will have, similar to the aviation industry, you will have a train operator like an airline, and you will have a train set provider. So there's actually three main players involved in how the system is going to be operated and maintained. And none of those three contracts I was just talking about has been let just yet, or basically issued. But the train set itself, it talks about, actually, it's the one that's available on the website. And so the handover activities are actually specified in those contracts.
All right. So, Mr. Bill Brown, I will slightly unmute you now just to understand if you're satisfied with the answer. Is the answer satisfying for your question?
Yeah, I just wanted to dig down a little deeper on how to ensure, you know, I guess that would be with language, how to ensure effective turnover. If there's a shared period, is there a way to enforce a shared period for the turnover, you know, intellectual knowledge transfer and all that kind of information? That was where I was kind of going with that.
Sounds clear.
So what we have is, before we officially hand it over, there's, as a very large system, you will have field testing. So all the types of testing anyways. You have production testing, factory testing, bring it to the field. You have what in our industry we call it static testing, where trains are not running. Then you have dynamic testings where trains are running. So during that time, we will have a shared, basically, the contractors are already using their equipment to test it. And also, you know, the term that's being used in our industry is pre-revenue testing. Even if everything now has been signed off, you have to train the people, you have to write the procedures, you have to train the people in the procedures. So before you go online to revenue service, you have pre-revenue testing. And that's really the overlap where you leave it to the contractor already and you watch them closely. But then there's a day where you say, okay, now it's all yours. Opening day, ribbon cutting, and here you go.
All right. So for the sake of time, I apologize, but we'll be moving to that's perfect. Thank you, Mr. Bill. So we'll moving to the next question. So RAM for systems, Mr. Kumar Katreddy has asked that RAM for systems and rolling stock is completely understandable. Need to have proactive and preventive maintenance for availability and calculated OTA. But RAM for infrastructure, the contractor would say, yes, I gave you a bridge, which will be there for the next 100 years. How do you verify that? Is it even verifiable? So are bridges verifiable, so to speak?
Yeah, and so you might recall that when we talked about infrastructure, that first we want the contractor to break down, you know, the system, quote unquote, and in this case, you know, the system would be a bridge. I could even, anyways, you could see that we have the superstructure and substructure. You break it down into all the various elements, and then the contractor is responsible to allocating the RAM requirements. So, for example, 50 years design life, 20-year design life, and you name it, and also the maintainability aspect. And so that is something that we want this really to be very tangible on the contractor side. What kind of drainage are you going to use? What kind of concrete you're going to use, basically writing the actual specifications. So if you have, let's say, a deck that requires 50 or 100-year design life, what type of products have been used in the past that prove that this can actually live up to 100 years, any lab testing that demonstrates it. And so just look into, let's say, for the Brooklyn Bridge in New York, it's already like what's it, like 1886, so 130 years or so old. So our, you know, infrastructure exists that's older than 100 years. So what we do is basically making sure that during the, you know, the specification of the system, everything flows down to the actual products that were being used. And then we basically make sure that the contractor is actually buying the right products, that we have you know, concrete pour testing, you name it. So it's being verified during design and validated during construction. And then all of this is actually being referenced using our V&V process, so we can refer to the actual inspection records, can refer to the actual design documents. So that is how it's being done in infrastructure. So you basically have to watch closely. You cannot go after the bridge has built and with a hammer and knock and hope you won't hear whether it's going to live or not for 100 years.
Perfect. So thank you so much. The last question from Ms. Wendy Owen. Then the question goes: you have used a balanced reliability apportionment approach across all the subsystems. Have you identified any RCIs, reliability critical items, at this stage?
Well, we actually we actually use the term critical items for something else. Let me just tell you quickly how we do this. Yeah. So we have what we call requirements and critical items are the ones that require special attention, specifically for certification at the end of the day. We use an requirements traceability approach for both, and the ones that are considered critical items are basically even to be certified. And so what we do on the RAM side is we have not considered RAM as part of those critical items because they don't require certification. What we do is basically what our client wants us to do is to leave maximum flexibility to the contractor. So what we do is we determine what are we trying to accomplish, performance requirements, and saying this is the design life, this is the maintainability. We provide a process we want the contractor to follow, in this case EN 51-6 and others, and now we leave it to the contractor to implement it. So we have not, to answer your question, we as the authority of program managers have not identified those. We leave it to the contractors to do that.
All right.
Not sure that answers the question, but
let's hope it answers it, and definitely emails can follow. We apologize for the sake of time, but we're cutting down the questions for now. I will switch over to Simon for closings. Thank you.
Great. Oh, well, thanks, Hamad and Rian, for your input here, and particularly Hamad, thank you. I know you're in Japan, and I know it's I think it's 2 a.m. Where you are, so thank you very much for staying up so late to
no problem.
It's a Friday. There we go. Good. And then just back to Oliver. Thank you, Oliver, again for your time. Again, an excellent presentation. So we will be uploading the recording of this entire webinar to the Transportation Working Group YouTube channel, and we'll be sharing that link on the TWG INCOSE website as well as our LinkedIn page. We'll also, Oliver, we normally share slides, so you and I should talk after this about whether you're comfortable sharing the slides or a subset of the slides with the making those available.
I'm fine.
To the membership.
I'm fine, but let's talk.
Okay. Good. Okay. Well, that's everything then. So thanks again to everybody who joined. I hope it was a good session for you as much as it was for us, and we look forward to having you at the next webinar.